Have you ever looked up at the sun and wondered, how will it all end? It's a question that has captivated humanity for centuries. We rely on our star for everything: light, warmth, life itself. But like all stars, our sun has a finite lifespan. And while we have a pretty good idea of its final act, the story of the sun's death is filled with fascinating uncertainties that astronomers are still trying to unravel. The grand finale for a star like our sun is a dramatic transformation into a red giant. This process begins deep within its core. For billions of years, the sun has been fusing hydrogen into helium, a nuclear reaction that generates the immense energy we feel every day. But this fuel won't last forever. In about 5 billion years, the hydrogen in the sun's core will run out. Without the outward pressure from fusion to counteract the immense force of gravity, the core will start to collapse. This collapse will cause the core to heat up and become incredibly dense. The heat will then ignite a shell of hydrogen surrounding the core, causing it to start fusing. This new burst of energy will push the sun's outer layers outward, causing it to swell up like a gigantic, fiery balloon. It will expand to hundreds of times its current size, transforming into what we call a red giant. Its surface will cool, giving it that characteristic reddish-orange glow. But here's the first major mystery: how big will it actually get? Our models give us a range, but the exact size is still a matter of debate. Will the sun's expanding atmosphere reach all the way to Earth's orbit? Will it completely swallow our planet whole? Or will it stop just short, leaving Earth as a scorched, barren rock, baked to a crisp by the intense heat? The fate of our home planet hangs in the balance of this cosmic uncertainty. Even if Earth isn't swallowed, it won't be a pleasant place to be. The sun's intense radiation will boil away our oceans and strip our atmosphere, leaving behind a lifeless, molten surface. So, either way, Earth's time as a habitable world will be long over. It's a sobering thought, but it highlights the powerful and dynamic nature of the universe we live in. After the red giant phase, the sun's story takes another dramatic turn. The core will continue to heat up until it's hot enough to fuse helium into carbon. This will provide a temporary new lease on life, but it's a short-lived one. Once the helium is gone, the sun's fate is sealed. Without any more fuel to burn, the fusion process will stop for good. At this point, the sun will become unstable. It will start to pulsate, rhythmically expanding and contracting, and in the process, it will shed its outer layers into space. These layers of gas, illuminated by the hot, exposed core, will create a breathtakingly beautiful structure known as a planetary nebula. These are some of the most stunning objects in the night sky. Intricate clouds of glowing gas that look like cosmic butterflies or ethereal bubbles. But this brings us to another big question. How long will this spectacular light show last? Planetary nebulae are fleeting phenomena on a cosmic timescale. They typically last for only a few tens of thousands of years before the gas dissipates into the vastness of interstellar space. The exact duration depends on factors like the speed at which the gas is ejected and the temperature of the central star. For our sun, we don't know precisely how long its final, beautiful creation will persist. And what about the core that's left behind? After shedding its outer layers, all that will remain of our once mighty sun is a superdense, Earth-sized remnant called a white dwarf. A white dwarf is essentially the smoldering ember of a dead star. It no longer generates heat through fusion. Instead, it just slowly radiates its leftover thermal energy into space, gradually cooling down over trillions of years. This leads to our final puzzle: how stable will this white dwarf be? A white dwarf is supported not by fusion but by a strange quantum mechanical pressure called electron degeneracy pressure. This pressure prevents the star from collapsing further under its own gravity. For a solitary star like our sun is expected to be, its white dwarf phase should be incredibly long and stable. It will simply cool and fade until it becomes a cold, dark, black dwarf, a process that will take longer than the current age of the universe. However, the universe is a dynamic place. What if our sun's white dwarf isn't alone? What if it's part of a binary system we haven't yet detected, or captures a rogue object in the distant future? If a white dwarf pulls material from a companion star, it can lead to spectacular explosions called novae. Or, if it accumulates enough mass to push it over a critical limit known as the Chandrasekhar limit, it can detonate in a cataclysmic type Ia supernova, an explosion so bright it can outshine an entire galaxy. While this is unlikely for our sun, the long-term stability of its final remnant isn't a complete certainty. So, while we know the broad strokes of our sun's demise: giant, planetary nebula, white dwarf, the specific details remain tantalizingly out of reach. Will it swallow the Earth? How long will its beautiful nebula last? How will it spend its final eons as a stellar remnant? These are the questions that drive astronomers to build better telescopes, refine their models, and peer deeper into the cosmos. The story of our sun's death is not just a story about the end of our solar system. It's a story about the life cycle of stars, the creation of new elements, and the constant evolution of the universe. By studying the fate of our own star, we learn more about our place in this vast and incredible cosmos. Thank you for joining me on this journey to the end of our sun. If you enjoyed this cosmic exploration, don't forget to like, share, and subscribe for more adventures into the unknown. See you next time.